Imagine reality as a vast tree that is constantly branching. Not once, not in some far-off future, but every instant. Each tiny quantum event, each flicker of a particle, could be another twig that splits into more twigs. If that image feels wild, you're not alone, but it's one of the most serious ways physicists have tried to make sense of quantum mechanics. Today we're going to walk through that idea step by step, in plain language. By the end you'll have a firm sense of what quantum particles do, why measurement is puzzling, what entanglement really means, and why some scientists believe the universe might literally be branching into parallel histories. Let's start small. At the tiniest scales, matter behaves in ways that challenge our everyday intuitions. Electrons and photons sometimes act like particles, little points that land in one place. Sometimes they act like waves, spread-out patterns that interfere and produce complex structures. Physicists captured this strangeness in a powerful mathematical tool called the wave function. The wave function gives probabilities. It tells you the likelihood of finding a particle in this place or that state. Before we measure anything, the system can be in a superposition, a technical term meaning multiple possible outcomes coexist in the quantum description. To make that concrete, imagine tossing a coin inside a closed box. Classically, the coin is either heads or tails, even if you don't look. In quantum land, the coin can be described as a superposition of heads and tails. Not that it's magically both in the same way a salad is both lettuce and tomato, but that the mathematics encodes both possibilities until an interaction causes a particular outcome to become the one you observe. How exactly that transition from many possibilities to one observed result happens? That's the measurement problem. It is one of the deepest conceptual puzzles in physics. One of the most famous demonstrations of quantum oddness is the double-slit experiment. Fire single particles, say electrons, toward a barrier with two narrow slits. Let them pass, and on a screen behind the barrier, you'll see an interference pattern typical of waves. It's as if each electron went through both slits and interfered with itself. But if you place detectors to find out which slit the electron passed through, the interference pattern disappears and you instead get two clumps. The act of measuring, the act of gathering which path information, changes the outcome. That's not merely an experimental quirk. It tells us something profound about the relationship between observation and quantum behavior. So how do physicists interpret this? There are several frameworks. The textbook approach, often called Copenhagen, treats the wave function as a tool for predicting probabilities, and says that when a measurement occurs, the wave function collapses to a single result. Collapse is a special rule you add to the dynamics. Before measurement, the wave function evolves smoothly. At measurement, it jumps. Many scientists are comfortable using this recipe because it works phenomenally well. But others worry it's unsatisfying because it introduces a sort of magic moment, a non-dynamical collapse, without specifying exactly when or why it happens. That's where alternative interpretations come in. One of the boldest is the many worlds interpretation. Proposed by Hugh Everett in the 1950s, many worlds suggests removing collapse altogether. The universal wave function always evolves according to the same clean, deterministic equations. When a measurement-like interaction happens, the total wave function evolves into a superposition of terms that no longer interfere. Each term corresponds to a different macroscopic outcome. Each term looks like a different world. In this picture, every possible quantum outcome is realized, but in different branches of reality. From the perspective of an individual observer embedded in one branch, you still experience a single definite result. From the perspective of the universal wave function, however, all outcomes exist. To visualize this, picture an enormous branching tree. Every quantum choice, even the tiny act of a photon bouncing differently on a beam splitter, is a fork. Most branches are almost identical. They differ by microfluctuations that never amplify. But the universe is vast and history is long, and microscopic differences sometimes cascade into macroscopic ones. Over time, trillions upon trillions of branches accumulate, painting a multiverse of near-identical and sometimes wildly different histories. Another core quantum phenomenon to understand here is entanglement. Two particles can be born together or interact and become entangled. Their properties become linked no matter how far apart they travel. Measure one particle, and you immediately find the corresponding property in the other. Experiments testing Bell inequalities show that these correlations cannot be explained by classical local variables alone. Entanglement is not a clue that signals travel faster than light. Rather, it tells us that the combined quantum description encodes correlations that defy classical separability. In many worlds' language, entanglement spreads the branching structure across systems and observers. When entangled systems are measured, branches split in ways that preserve their correlations across the new branches. A crucial question is whether many worlds makes different predictions than other interpretations. For everyday quantum experiments, it doesn't. It reproduces the same numbers. That empirical equivalence is why many worlds is often called an interpretation. It's a different story about what's really happening behind the equations rather than a new set of testable rules. Supporters praise it for conceptual clarity. You don't add an ad hoc collapse rule, you simply take the equations literally. Critics ask how probability emerges if every outcome happens. If there's a branch for every possibility, why do we observe statistical frequencies in line with the Born rule? There are proposed derivations that aim to recover the usual probabilities within many worlds, but philosophical debate continues. What would it mean for us if branching were real? Practically, most branches differ only by microscopic details. For everyday decision-making and technology, the world you and I experience behaves according to standard quantum probabilities. But as a thought experiment, the branching view provides a striking picture. Somewhere in the multiverse, tiny differences accumulate into worlds where different discoveries were made, different political choices happened, or different technologies emerged. Whether those branches matter ethically or personally is a deep philosophical question. If an alternate branch contains a version of you who made different life choices, does that affect your own moral responsibilities? Most working scientists treat those as interesting but remote philosophical repercussions. They don't change how labs design experiments or how engineers build devices. It's also worth emphasizing the practical side. Regardless of interpretation, quantum mechanics is an extraordinarily well-tested theory. It underlies transistors, lasers, MRI machines, and the race to build powerful quantum computers. Interpretations don't alter the predictive machinery that produces those technologies. Interpretations are about what the formalism means when we take it seriously, so where might future progress come from? On the experimental front, physicists keep pushing the boundaries, creating larger-scale quantum superpositions, improving Bell tests, and probing quantum coherence in new regimes. Advances in quantum information and computing also change the kinds of experiments we can even imagine. On the theoretical front, progress could come from a deeper theory that unifies quantum mechanics with gravity or from clarity about probability and decoherence. Until then, multiple ways of understanding the same mathematics coexist. If this topic has piqued your curiosity, consider this your invitation to keep exploring. Quantum mechanics reshapes how we think about chance, observation, and reality itself. Whether you prefer a compact pragmatic rulebook that collapses probabilities into outcomes, or a grand branching multiverse of all possibilities, both views force us to confront how strange the universe really is. If this idea bent your brain and you want more deep dives that make strange physics feel surprisingly clear, subscribe for more mind-bending science and hypotheticals about reality. Hit the bell so you don't miss our next exploration.